streaming. Okay, there we go. And yesterday I forgot to bring my USB dongle, so I wasn't able to record my classes yesterday. So I had to use my phone to do the audio recording, and then the app is still recording the video. And then when I got home, actually this morning, I downloaded both the video and also the audio, and then I used a program to kind of slide those things and cut the portions and then remake the video. Uh huh. Yep. So that was okay. I know how to do that sort of stuff. Not the first time. All right. So our recorder is on, and also the computer crashed last evening when I was teaching my 2-hour class. So the computer crashed, but the recorder, the audio recording was still going on. So I had several clips of videos to kind of splice together, and then combine it with the audio. So it was kind of fun to do all that, editing this morning. Okay, so cool. So what we're going to do is we are already done with subroutines. So we'll go ahead and just take a look at some examples and make sure that we already understand all of those concepts, because I just want to make sure that you guys do not have any further questions about those things. The first one is just how to return a value. Okay, so in this case, let's say we have 30, okay, as the name of the subroutine, and all it's going to do is to return the numerical value of 30. Okay, do we know how to implement a subroutine like this? The answer is no, no, same way as usual. Okay, so what is the key concept of this? How do we get this? Okay, let's roll back a little bit because of the long break. So we'll roll back a little bit and say we have a subroutine called do nothing, like that. Okay. Do we know how to implement do nothing using TTP ASM? In other words, do we know how to return? That's the only thing it's going to do is to return, right? So do we know how to return from a subroutine? Okay, so there's a JMP with a register, not I. Okay, it's not going to use JMP I because JMP I is only good if you are going to the same place every single time. But when you're returning from a subroutine, it depends on where your caller was, right? So you're only returning to where the caller left off, okay? And that place is going to change. So you're not going to use a JMPI, you're going to use a JMP with a register. So now the question is, how do you get the return address into the register? Does anyone want to kind of give it a try? Okay. No one wants to give it a try? All right, so what we'll do is on the side here, we're going to implement do nothing as a subroutine in TTP ASM. So the label do nothing is the same as the name of the subroutine. That is the entry point of the subroutine. There's nothing to do in the subroutine, so if you prefer, you can stick a no up here just to emphasize that we are not doing anything. But then when it's time to return, the return address is on the stack. And it is also going to be the last thing that the caller is pushing on the stack. So that means you can retrieve the return address by using an LD instruction. So we're going to use LD, and in this case, register A can be used. It's fine, because the subroutine itself has a void return type, which means it's not returning a particular value. So we can use register A, B, or C for this purpose. There's no particular reason why not to use register A. So this is retrieving the return address. Okay, I'll just comment it here. Retrieve return address from stack. And then we have increment D. Can someone explain why am I incrementing register D, which is the stack pointer? What is that doing? Go ahead. Why am I increasing the stack pointer? Deallocating, very good. Okay, so we make use of the return address and we're deallocating the byte on the stack. Okay, so we deallocate the return address from the stack, so that byte is now freed. And then we have a JMP-A instruction to continue execution. Continue execution in the caller, basically right after the call itself. So that's how we implement do nothing. It's really just 3 instructions at the end to retrieve the return address, to free up that byte on the stack, and then to continue execution in the caller. Do we have any questions about do nothing? Okay. Yep.
So just for, I don't know if it even is useful, but if we were to like change the register A,
Uh-huh.
would we lose the return address like altogether later on?
Return address.
So you know how we push the return address from the stack to register A. So LD
Uh-huh.
A, so that's retrieving the return address from the stack.
Yes.
And then we do the increment to deallocate that from the stack.
We're deallocating the byte on the stack.
Right.
But the return address is already in register A at this point.
Right. So if we were to overwrite register A, that's a different instruction. Will we lose that return?
Yes, we would.
Okay.
Yep. But in this case, it's not going to be a problem because do nothing does not return a value. So register A is not going to be used to specify a return value because there's no return value. Yep. All right. So what about 30? How are we going to implement 30? Well, 30 is going to be about the same. Okay. The only difference is it has a return value. To specify the return value, we use register A. That is a convention. Okay. So register A specifies the return value. So it is important to differentiate a return address from a return value. A return address is a location in the caller that I have to go back to continue execution. That's a return address. A return value is a C concept, C and C++ concept. It is just whatever value you're returning based on the type of a subroutine. Okay, so those two concepts are related, but they are definitely not the same. Okay, one concept is visible in C and C++, and that's the return value concept. The concept of a return address is not visible in C and C++. You never have to actually specify the return address or explicitly make use of the return address in a high-level programming language. You just say call, and then automatically at the end of a subroutine, it automatically returns. But in assembly programming, we do not have the luxury of, oh, these things are all automatic. Okay, we have everything being exposed in the case of assembly language programming. Okay, so if you look at 30, we're not quite done yet because now we also have to retrieve the return address, but this time it is retrieved into register B because register A is already used for that special purpose of specifying the return value. So this time we have to use register B or C, okay? It doesn't matter which one we use as long as it is used consistently. But the 3 instructions are pretty much the same except they are using register B instead of register A in this case. But it's still the same thing. We still have to retrieve the return address. We still have to increase the stack pointer because we are deallocating that byte on the stack. And we also have to continue execution in the caller using the JMP-B instruction this time because the return address was retrieved into register B. So is that okay with 30? Okay, all right. So what about this one here? Okay, we'll use uint underscore t for unsigned integer, and we'll call this one pre-increment. Okay, pre-increment is going to need the address of an 8-bit unsigned integer. Okay, so we'll call it pointer. So the way to do this, okay, so let me specify what it does, okay? So pre-inc the address of x is really the same thing, does the same as x++. So we'll make it post increment. Sorry about that. There we go. Okay. So what is post increment? Post increment means the expression itself, which is x plus plus, returns the value of x prior to the increment. But the side effect is x is actually incremented. Is that okay? Because that's a concept that you should have learned in C++ in CISP 360. Is that okay or not? Yes? Okay. So if you want to use a subroutine to implement exactly the same thing, it can be done. Okay, it's just there are several ways to do it. Okay, there's the obvious way, and then there's the not so obvious way. So the obvious way to do it is to store the value of whatever pointer points to into a local variable, and then you increment whatever PTR points to. So you basically, I'm just thinking about what is the best way to describe this. Um, well, okay, this is what you're going to do in the next line, and what you're returning is x. So that is kind of underneath x plus plus or post increment. This is what it's doing. It's taking a snapshot of x before the increment, and then it increases x by 1, but the value of the expression x plus plus was the original value of x before the increment. As opposed to pre-increment or plus plus x is returning the value of x after the increment. Is that okay? Really important concept that you should learn in C and C++, because even if you decide not to use confusing operators like this, you will find plenty of code out there that will make use of the concept of post increment in this case. Okay, so just because you're not going to use it doesn't mean you do not have to understand it, because you probably will encounter somebody else using this kind of code, so it is important to understand it at least. Okay. All right. So we'll look at this and go like, well, but how do we implement this in assembly? Oh, I put it into the wrong side. That's okay. We'll just fix that, copy and paste it here, and then continue on this side. Okay. So this is post increment. And this time I'm going to use the new feature of the assembler because we can now define labels in a different way. So it's going to be a little bit handy in this case. So the way I'm going to specify the label is going to start with my local variable x. Okay. So my local variable x, I will define it to be 0. Okay. In other words, this is going to be 0 bytes from where register D points to. Okay, when I'm done setting up the stack, this is where the stack pointer is going to be pointing to. Above that is going to be the return address. So the return address is x1 plus. Remember, it's postfix, so you specify the things that you need to operate on, and then you perform the operation. So we basically, x1 plus is the postfix notation of x plus 1. That's all it is. But because x is 0, well, all we are really saying is return address is 1. That is the offset from where the stack pointer points to compared to where the return address is going to be on the stack. So we'll also make that statement here. 1 byte from where D points to. And then above that would be my parameter. So in this case, my parameter is called PTR or pointer. So PTR is going to be return address plus 1. But in postfix, it is 1 plus. Okay. So this is 2 bytes from where D points to. Okay. So these are handy, symbolic names that I have defined for items on the stack. The first thing we need to do here is to decrement D. Okay, so we are allocating for local variable x here. So what the stack is going to look like right now at this point on line 18 is the highest byte, or the byte at the highest location that I need to know about, is going to be pointer. That's the parameter. It was pushed by the caller. The next byte down is going to be the return address, which was also pushed by the caller. And then the next byte down, which is what the stack pointer is pointing to right now at this point, is my local variable x. That was the responsibility of the subroutine itself, not the responsibility of the caller. Is that okay? So if you were to draw a picture of the stack, okay, what it's going to look like is pointer is going to be here. The next byte down is the return address. The next byte down is going to be local variable x. And guess what? Your register D, your stack pointer, should be pointing at local variable x right now at this point. And it's not initialized. Is that okay? All right. Okay, so we are just going to follow the C code here. The first thing we do is we try to dereference pointer PTR, get whatever it's pointing to, and then copy that to my local variable x. So let's go ahead and check out what we need to do here. There are many ways to do it, but now that we have these symbolic names, we can use a particular approach that is really structured. So what we do is we load the label corresponding to the item that we want into register C. So in this case, it's my parameter PTR. So we use a LDI C PTR so that C becomes basically just 2. Okay? And then what we're going to do is to add CD. So if I were to comment what is the result of each operation, after this, I don't have to deal with this keyboard, after a day or so. Then I can get back to my nice Lenovo keyboard with that little touch point thingy in the middle. Okay, so at this point, C is nothing more than just the constant of 2. But at this point, C is whatever register D is, which is our stack pointer, plus 2. But that, by the way, is also the address of the parameter pointer. Is that okay? Okay, because this is how we compute the address of items on the stack. Everything is relative to the stack pointer. Is that okay? All right, okay. Well, but that's not what we want, because on this side, the first thing we need to do is to dereference the address of pointer so we can get to pointer. Okay? So we say, oops, wrong side. So we say LDC in parentheses C. So C is now the dereference portion of the address of pointer. Oh, that's just a really clumsy way of saying pointer. Is that making any sense? Okay. If it's not making any sense, you need to let me know so that I can, explain that. Okay, but that's even not what I want, because what I really want is what it points to. I get the pointer now, but I want to know what pointer is pointing to, so I need to dereference it one more time. So we have another LDCC. So the C is now whatever pointer points to. Now that is what I want on the right-hand side of line 14. But what about the left-hand side? Where am I going to store that? I'm going to store that into X. What is still pointing at X at this point? Register D, my stack pointer. All of these calculations do not change register D. So register D is still pointing to my local variable X. Oh, that is really handy, because now I can just say, oh, okay, let's do a st instruction to whatever D points to, and we'll store whatever C has to that place. So in this case, X, which is what D is pointing to, is now getting whatever the pointer is pointing to. And therefore, we finish the assignment statement on line 14 of the C code. Are we good so far? Okay. What about the next one? Ooh, the next one looks kind of ugly, because we have to add 1 to whatever PTR is pointing to, and then we store it back into PTR. Okay. So we'll separate it into 2 steps. The first thing is, oh, C is still whatever PTR points to. So if I increment C, then C is now whatever PTR points to plus 1. That's my right-hand side. That's kind of handy. But now I need to store it back to whatever pointer points to. So there are two ways to do this. I can just recalculate everything using a different register. Let's say register A or register B. Both are okay. Or I can cheat a little bit and take a snapshot of a register from earlier. So what I need to get to is PTR. I need to put PTR into a register, and C does equal to PTR at this point. So what I'm going to do is I'm going to cheat here, and I'll say, oh, let's go ahead and copy register C to, let's say, register B. Okay, so that register B is also the same thing as pointer, which is my parameter. So now I can reuse register B here and just say, oh, okay, just go ahead and store to whatever register B is pointing to, the right hand side of the assignment, which is whatever pointer points to +1. So in this case, it becomes whatever PTR points to gets whatever PTR points to +1. Are there any questions at this point? Yep.
Since we stored pointer into X, could we have possibly done that copy for register D instead of copy to register D from C?
Say that one more time.
Since we stored pointer into register into X, right?
You mean here?
Yeah.
Uh-huh.
Possibly have done a copy from register D.
You mean here?
Yeah. As in, you know how so we did a copy from register C into B, right? Since doesn't
Correct.
B also contain the same? Isn't X?
No, because this is incremented. C is incremented from compared to here.
Okay. Right. Okay.
And then the ST instruction can only have one indirection. So it only has an indirection with the destination, but not with the source.
Okay. Gotcha.
All right, one more thing to do. This is the second assignment statement, which is line 15. So now we have to deal with line 16, which is returning the value of x. That is really easy. We just say LDA with D. Because register D is still pointing to local variable x. So now we specify the return value of x. We are all done. So we just go like LD, pick one of the registers B or C, doesn't matter which one. So we can say register B, whatever D points to. So this time we are retrieve return address, increment D, so that we can deallocate return address from stack, and then JMPB, so that we can now continue execution in the caller. So is that okay so far? Because the third example of post increment is actually using quite a few concepts that we have already talked about in this class, including parameters, local variables, getting to dereference a pointer, and so on. Yes. Say that one more time. We have to deallocate the local variable. Very good. Because otherwise we'll be using the local variable as a return address. Okay. Good point. Okay. So so what he's pointing out was line 32 is copying whatever register D points to A, and that was X. And then on line 34, we're copying the same thing over to register B, but this time we are treating it as a return address. So that is incorrect because I forgot to do one thing. I forgot an increment D here to deallocate the local variable X. So that was a good catch. Thank you. Good job. Now, if I did miss line 33, the program is not going to work because it will return to the wrong place. So how are you going to debug a program when it's misbehaving because of that reason? What would be the symptom? How can you tell that the program is not working? Yep. Well, not entirely random. It will go to the location based on X. Okay, so but it will go to the wrong place. Okay, most likely than not, it's going to go to the wrong place. But where it's going back to, in terms of the caller, okay, I put it in quotes because it's really not a caller anymore, is based on the value of X.
which is most likely a 0.
What?
Which is most likely points to a door.
It depends on what pointer points to, because X is based on what pointer points to. So, but regardless, the symptom, the immediate symptom is the subroutine returns to the wrong place. So using the simulator, how can you tell that the subroutine is returning to the wrong place? What do you track so they can tell that the subroutine is returning to the wrong place? Yep, you track the program counter. Okay, so do you guys want an example? Like when this thing doesn't work, how to track it down so that you know how to debug it. Okay, let's do that. So the subroutine itself, okay, so I'm going to comment out this line here to intentionally put the bug back into the program so that it does not behave correctly, okay? But to turn this into an actual program, we need a main in order to call the subroutine. So we'll go ahead and write the main subroutine here. So before we get into main, we have to initialize the stack pointer. LDI D0 can do that. Okay, so we initialize the stack pointer. And then here's main. And we'll need a local variable in main so that we can actually do a post increment of. So, okay, let me do this side by side again. But this time we're dealing with main. Oh, there we go. So we have main. And inside main, we have two local variables. Okay, so we have x and y as local variables of main. We'll get x to pre-initialize to a particular value. Let's say it's 80 in decimal. And then we'll say y is post increment of x. Okay, and you have to pass the address of x because the parameter is supposed to be a pointer to an unsigned a-bit integer. And that's it. Okay, that's the entire main. Switch back to assembly code. So now we want to implement main in assembly. We need to decrement d twice. Okay, so this one is to allocate for x. Decrement one more time. This time it's allocating for local variable y. So if I want to use symbolic names to represent what is in main, then y as a label, which is denoting, where is local variable y compared to where the stack pointer is pointing to, this would be 0 because the stack pointer is pointing to y exactly. X is going to be 1 byte above that, so it's going to be y1 plus or y plus 1. And we don't have anything else. Main does not have a return address because that's basically where you start execution from. So there's no return address. There are no parameters either. Okay. Okay. So the first thing we need to do in main is to initialize x with 80. Okay. I could have done it, right here when d is still pointing to x, but that would not be the same thing as implementing the C code just like this. So we'll do it the hard way, which is to calculate it using the sequence of code that we have talked about earlier. We load register C with the displacement, which is represented by the label x now, and then we add the stack pointer to C so that C is now pointing to local variable x. So once again, I'm going to annotate what the registers are containing. So in this case, x is C, register C has 1. Now register C has d plus 1, which turns out to be the address of local variable x. And we have to store 80 into that location. So we use LDI, let's say A80. So the register A is exactly the constant of 80. And then we store that to whatever C is pointing to. So we use a STCA. So this time x, okay, to To be more exact, this is what it's doing. Okay, because register C has the address of X, so there's the address of X, but store dereferences register C. So that's why we have a dereference operator here. And then what we use to override that location is just register A, and register A has a value of 80. So we are overriding local variable X with 80 in this case. So that would be the first line, or line 22 in main. The second line in main wants to pass the address of X as a parameter. Well, guess what? The address of X is still in register C, so that's kind of handy. So this time we'll say decrement D. We are allocating param1. There's only one parameter to post inc, but we'll say param1 of post inc. And then we'll do a st instruction, store to whatever the stack pointer points to, C. So we are basically pushing the address of X on the stack right now as the only parameter to post increment. And then we decrement D again. This time we are allocating for the return address. And then we have to specify what the return address is using the LDI instruction. I can use any one of the registers now, A, B, or C. It doesn't really matter which one. So I'm going to put it into register A. But typically, remember, we specify a return address as a label, down, below the JMPI instruction. I'm going to do it in a slightly different way now. Okay, you guys have seen it already, but we'll do it in a slightly different way, which is .6+. What does that mean? Well, the dot is referring to the address of the instruction of the same line. So the dot is referring to the address of the first byte of the LDI instruction. 6, well, that's just a constant value of 6, and then plus. So this is basically .6+ is basically saying, oh, the address that is 6 bytes away from the LDI instruction. That's what it's saying. Why is that particularly of interest to us? Well, let's figure out what else we have to do. The typical sequence of operations that we have to do. We store to whatever the stack pointer points to, register A. So this is pushing the return address. And then after that, we have to, let's see, 1, 2, 3. Okay, I think it's only 5 this time. Yeah, it's only 5 this time because JMPI can occur here, and that's the one that's going to call post inc. And the reason why it's 6 is because I typically put the decrement below the LDI instruction. So if I preserve that, then the 6 will still be correct. There we go. Where post inc should return to. Okay. So let's do some counting here. When post inc as a subroutine returns, it should return to right after the JMPI instruction. What happens when it returns to the JMPI instruction itself? And the call is going to happen again, right? That's not what it's supposed to do. It's supposed to go to 1 right after the JMPI instruction. So if you do the counting, how many bytes do you think LDI is going to take up? The LDI instruction takes up 2 bytes. The first byte is the actual opcode that is decoded, to an address of the ROM inside the processor. The second byte specifies what constant, what value do you want to put into register A. So it takes up 2 bytes. So we have LDI instruction taking up 2 bytes. The decrement D instruction takes up only 1 byte. The ST instruction takes up only 1 byte. What about the JMPI instruction? Takes up 2 bytes. So we have 2 plus 1 plus 1 plus 2. Altogether, 6 bytes. So when we specify 6 bytes after the LDI instruction, we are specifying exactly where the subroutine is supposed to return to. That is our return address. Okay? So this is equivalent to defining a label right after JMPI and then refer to the label in the LDI instruction. It would be exactly the same thing. But the nice thing about this approach is you don't need to define extra labels for that purpose. And because we are not using extra labels, it is also going to remove the possibility of using the wrong label. Because if you're using a label and you have a lot of calls, in your subroutines, if you use a wrong label, the assembler cannot tell. The assembler cannot say, oh, you're supposed to use that label and not that label over there. As long as both labels are defined, the assembler cannot tell you whether you're using the right label or not. This method does not rely on any name of labeling. So that's why it is a more reliable way to do things, as long as you keep the sequence of instructions exactly like this every single time you make a call to a subroutine. Is that okay? All right? Okay. So when the subroutine returns to this place here, okay, so I'm going to continue coding after this. We got a few things to do. The first thing we need to do is to increment D, because the parameter is still on the stack. It is up to the caller to deallocate the parameter. So we now want to deallocate the parameter of post_inc because it's still on the stack. So after that, the stack would look, the stack pointer would be pointing to Y again. So we just need an st instruction. So we store to whatever D is pointing to the result of post increment. So which register should I use as the second operand of the store instruction? Which register contains the return value of post_inc? Register A, very good. Okay, that's a convention. So this is the same thing as Y getting the result of the call. And we should be all done at this point. Well, not quite, okay? Because if main were a real subroutine, we also have to deallocate the two local variables. So this increment is deallocating local variable Y, and then this increment is deallocating local variable X. And now we are done. Okay, the stack is fully balanced. It should be back to 0 at this point. Do we have any questions about this code so far? Just main itself. Mm-hmm.
Question about the 0.6 plus.
Uh-huh.
So basically, it just tells the compiler to read the 6 line below the 6 bytes below.
6 bytes, right. So the dot refers to the address of the current line. Okay, so the first byte of the LDI instruction, or the address of that byte, is represented by the dot. And then 6 bytes after that would be the address of the increment instruction.
What if you change it to 6 minus? Will it go?
Then it will be 6 bytes before the current address.
What if you take out the point?
Take out a point?
Yeah, it's just 6 plus.
If you give it 6 plus, then it is going to be just 6. Because the way I interpret the plus is if you have at least two items, it will add those 2 items on the stack. But if you only have one, it becomes a unary plus, which is basically not do anything. Yep. Mm-hmm. All right, so I think we got this program pretty much done. So we'll copy and paste it into the assembler, and then we'll give it a try. Okay, remember it's supposed to be incorrect, okay, because I commented out the instruction that I missed out in the, to begin with. So let's go ahead and give this a try. And using the wrong account here. The new computer is going to be really nice compared to this one. It's going to have 16 gigs of RAM instead of 4. Huh?
How much was it?
It was a little spendy, about $1,400.
Did you buy it on Black Friday?
Yeah, yeah. And so I saved $500 already because of that. But I only buy a new computer like every 5 or 6 years, so.
Is that gonna be as durable as this one?
No, it's gonna be it's a 2-in-1, so it comes with a stylus. So it might replace both this and also the tablet that I have that I'm using on the side. Haven't really quite decided the workflow yet, because to use the pen or the stylus, yeah, you don't want it to be like this. You want it to be flat. Then you can actually write on it. So switching between typing and handwriting, it's just one step. Just have to kind of fold the screen down and then fold it back up. But I think that's going to improve efficiency, so I don't have to kind of go between the two devices.
Maybe they can give you a keyboard you can just plug it in from the beginning, so you can fold your tablet, your computer to tablet mode and type at the same time.
It already has a keyboard. It's a 2-in-1.
Oh, I know, but when you flip it around to the position where you're using tablet, a lot
No.
of times the keyboard is locked.
Is that the case? Does it turn off the keyboard?
A lot of them, what happens is the keyboard flips around
Uh-huh.
and then it goes under the screen.
Well, I'm going to run Linux on it, so I think I might have control over whether the keyboard will still be working or not. But that's a good point. If it mechanically turns off the keyboard, like it loses contact with the keyboard, then I probably would have to use an external keyboard to make it work. Okay. Getting Linux installed and get it to work, it's going to be an interesting process too. All right, so whoops, okay. There we go. And we won't be looking at the hourglass or the progress bar like this. Or looking at the loading. There we go, we are all done. And then we look at the RAM file. Do we have any errors? No errors. Okay, very good. So we download as CSV. And let's see, how should we call this? Post Inc. There we go. And then we'll start up Logisim. And then load the program into here. And it's called Post Inc. There we go. All right, so we are ready to run the program. And this program, by the way, is intentionally incorrect. Okay. Did I put in the last halt instruction in main? Okay, I did. Thank you. All right. So we're gonna do some logging. Okay. So we'll log at least the program counter. We'll log register D. So, this is register D. We'll also log the stack. Okay, we'll find out what is happening on the stack itself. And the stack is in RAM. And we'll try to figure out how many locations to log. So we have local variable y, local variable x of main, local variable y of main, the parameter that we pass to post inc, the return address that we push on the stack to call the subroutine post inc. Then we have the local variable x in post inc. So we need at least 5 bytes on the stack. Okay, I think that's it. I think it's only 5 bytes. So we'll go ahead and log 6 locations on the stack, just in case my estimate is incorrect. So 1, 2, 3, 4, 5, 6 bytes. And then we'll change all of these to base 16. Okay. I might give this computer to the daycare person who used to take care of my kids. I just got a call from her yesterday or day before yesterday to get her printer to work. As it turned out, it wasn't a printer issue. It wasn't a driver issue. She ran out of space, RAM on her computer. She was running Windows XP with 1 gig of RAM. So the fact of opening Firefox to get to Outlook and print a PDF from Outlook at the same time used maybe 2.4 gigabytes of memory. So the whole thing was swapping things in and out the entire time. And it just died, okay? So I think, this computer, can be repurposed, so that she can have a better computer. I mean, 4 gigs of RAM compared to 1 is a 4-fold increase.
And she able to use Linux?
Huh? Well, 1 gig is going to be pushing it even in Linux.
Does she understand how to use the Linux model?
Probably not. But I still have Windows on this one. Not XP. I have Windows. I actually have Windows 10 installed on this one. It works. It works okay. But 4 gigs is not really. It doesn't leave you a lot of room when you're running Windows 10. But it will still work. Okay, so we got the program counter, we got the stack pointer, and then we got 6 locations in RAM. What else should I be logging? I think that's all we need, because we just need to know that the return did not happen the way it's supposed to. Okay, so I think we got enough here. So we go to File, we specify where we want to keep all the logs in. So we say posting.tsv. Close this window, Control K, run the program, and you can see how it's sliding through the 00s because it didn't end where it's supposed to, so it went to the wrong place and then start executing all the 00s, which were basically no op instructions. Okay, so now it has stopped. Control K to stop the entire thing, and we'll close Logisim, and then we'll go back to a spreadsheet to take a look at the log. And that's going to be in temp postinc.tsv. Okay. And the trick is to treat everything as text, so there's no conversion into numerical value. Okay. Click OK. All right, and then we'll rename several items here. This is our stack pointer. This is what is at location 255, 254, oops, wrong side, 253, 252, 251, and 250. There we go. There we go. Okay. So when you look at the execution of this program, we can kind of tell that it's not doing it right because the program counter kept going. Okay. When we go to the assembler, okay, let me switch back to the assembler. The program is not really that long. Okay. When you go to the best way to look is to go to the assemble tab, and then just kind of scroll down to until the program has ended. So the last line is row 60. And when you look at the address, it's only 2D, okay? So 2D is the address of the very last instruction of the entire program, okay? It should not get past 2D. The program counter should never get past 2E, which is 1 byte after 2D. But when we go back to the log, you can see, okay, let me do this trick here first. So I'm going to split the screen so that you can always keep track of the column header. But you can see how the program counter just kind of kept going. Okay, so that's the first sign that something did not go right, because the program counter kept going. So now the question is, well, where did it go to keep going, to basically La La Land? So you scroll back until it goes, until the sequence, until you get back to the beginning of the sequence, and you can see how it went from 2E all the way to 50. Is that okay? Then go like, that doesn't seem right, okay? So what is at location 2D that is causing the program to continue execution at location 50? Okay? So you go back to the assembler, okay, because the assembler is where you can find out what instruction is where. So you go to location 2D, okay, this is location 2D, and is corresponding to the JMPB instruction at the end of a subroutine. So the fact that you continue execution at 50 can only be because B as a register has 50 in hexadecimal in it. And go like, that doesn't seem right. It's supposed to go back to main, which is a earlier location. Why is B getting, a 50 instead? So you go backwards in your program. Okay, so register B was loaded by this load instruction, and the stack pointer is still register D has to be pointing to 50 at that time. So you go back to the trace, okay, and this time you pay attention to the stack pointer. The stack pointer is pointing to a location FC, which is 254, and location 254 definitely has the wrong address. Okay, it has location 51 in it instead of let's see, why would it jump to 50 instead of 51? I think these got increased afterwards. No, cannot be. Is that the second round already? No. Get back here. Now I cannot explain why it's going to location 50 instead of 51, because I didn't track register B. So let's see. We put the store is done here, and then register D never changed after that until here. So FC is not where we should be looking at. Okay, it's right here. I miscalculated. FC is actually location 252, and then FB is location 250, and that's where the 50 is. So my mistake, I converted the base 10 to base 16 incorrectly. So 252 is FC, but the load into register B was done earlier when it was here. So at that time, the stack pointer was pointing to location FB, which corresponds to location 251, which had the value of 50. Okay, so that accounts for why it's jumping to location 50. Okay. But now the question is, well, I know 50 is the wrong place that it's supposed to go to, but where was it supposed to go back to? That becomes the next question. Okay. And from the assembler, can we find out where it's supposed to go back to? Okay, it has to be something in main, right? So in main, this is loading the return address, and it's supposed to return to this increment instruction. So the location it's supposed to go back to is location 12 in hexadecimal. When you look at the trace, that thing is here. The return address is clearly on the stack, but I'm using the wrong item to put into the register. What I put into the register, as if it is a return address, is this byte here. In other words, it's off by 1. Well, why is it off by 1? Because I forgot to increment the stack pointer. when I forgot to increment the stack pointer was still pointing to this location when I copy whatever the stack pointer points to into register B. If I remember to increment the stack pointer, then it would have loaded the content of this location into register B, then it would be going back to the right location, which is location 1, 2 in the program. Is that okay? So is that kind of, does it help to illustrate how to debug a program when you're dealing with a stack and calling subroutines and returning and stuff like that? Okay? So the trace is really important because you can look at the trace, you can print it out, you can store it into a file and analyze it later on. If you use a table in Logisim, the moment you exit out of Logisim, that table is gone. So you cannot really do any post-analysis after you close the application. Okay, any questions about this particular session? No particular question? Okay. So we'll go ahead and fix the program and then see the correct behavior of this program. So how many people are looking forward to programming in assembly language in your career as a job?
C, please.
Well, that's good news to me, because it means if I ever want to become a developer again, there will be fewer competition, because this is the kind of stuff that I like to do. All right, so this is the instruction that I commented out. So we'll put it back in. Okay, so we put it back in, and the assembler is doing its thing. And then we go back to the RAM file, re-download this stuff as post inc again. And yes, we want to replace. Okay, and then we have to restart Logisim. And reload the program. And then do the logging again. So we go to logging. Same stuff. We will log the program counter. We'll log the stack pointer. And we'll also log the 6 locations in RAM, just like last time. So this way, we can actually compare and contrast the execution of these 2 programs. And we'll log all 6 locations, even though I'm pretty sure only 5 of those locations will be used. Okay. Unfortunately, there's no way to multiple select and then change all the radix at the same time. And then we'll specify the log file as postinc1.tsv. There we go. Control K to run the program. It's all done. And then we'll close Logisim and open this file in the spreadsheet. So open postinc1.tsv. There we go. This is our stack pointer. Okay, I'm just going to be a little bit lazy by copying these over here. and then reformatting all 5 columns at the same time. Okay, so we'll take a look at this log, and we'll just do a quick scan first. Okay, so do a quick scan, and the program counter is within the correct range. Okay, it never exceeded the range that it's supposed to go. So, and we reach the halt instruction as expected. So by the time we get to the halt instruction, we kind of want to focus on this row here. In other words, when the program terminates, what are we seeing? What is in the stack pointer, what is in RAM, and what is the program counter? The program counter is at location 17, which means the last opcode is at location 16, because the program counter increments during the decode cycle of executing an instruction. So by the time the effect of the instruction is visible, the program counter is already 1 past the location or the address of the instruction. So we double check that, okay? So we want to double check using the assembler and say, and ask, is location 16 in hexadecimal our halt instruction? And the answer is, yep, that is the case. So that's a comforting thought because the program seems to terminate correctly. What else should we looking at? What else should we be looking at? We should be looking at the stack pointer. The stack pointer is back to 0. That's good because the stack is now balanced. Okay, we are not keeping anything else on the stack when nothing is supposed to be on the stack at this point. Okay. And then we check out the variables, the stuff that is that's on the stack, and something is not right. It went from 5.1 back to 5.0. So I stored the byte to the wrong location. Okay, so the program didn't work after all, because when you look at the locations, location 255 is supposed to be X. Location 254 is supposed to be Y. They are supposed to be different, but you can see how one column is not changed at all. So that means the code was not implemented correctly. All right, so we'll go ahead and fix the code again. And the important part is to look at the C code and the assembly code side by side. So in main, we're supposed to put 80 into X, and X is 1 plus whatever the stack pointer points to. So that should have stored decrement, okay. Y is what the stack pointer points to, and then X being 1 off is where the variable is. So we can double check that, okay. So instead of staring at the code, we can go back to the spreadsheet and see if it was stored in the right place. So it was not. You can see how 50 or 50 in hexadecimal was stored in location 254 instead of 255. Okay. Okay, so we allocate for X first. So X is the one with a higher location. Then we allocate for Y, so Y is the one with a lower location. So that seems okay to me. So we load X into C. We add the stack pointer to C. And then we store 80 in decimal into whatever C points to. So 255, 254. Yep. The LDI instruction has 2 bytes. The dot refers to the address of the first of the 2 bytes. Yeah, that would not impact this code here. Yep. So register C has 1, And the register C then has D plus 1. D should be 254 at this point, so 254 plus 1 should be 255. Well, we can also double check on the stack pointer. So the stack pointer is FE by the time we got here. And that is correct because it was initialized, the stack pointer was 0. It decrements twice to FE, but FE plus 1 should be FF. So this column should be the one changed to 50 instead of this column here. Line 1? You mean here? Okay, well, the stack pointer is initialized correctly. It should be 0 because it's 1 byte past the end of the entire RAM. So it's 1 byte past the location 255. So that is actually correct. I didn't log register C, so that's kind of the issue here because I can't see how register C got changed. I'm suspecting X is not resolved correctly. That could be one of the reasons. So we can go into the assembler to check that. And then we ask, there are 2 ways to check that. Yep, okay. So X is not resolved correctly. For whatever reason, the assembler thinks X is 0, so that's why it was using the wrong offset. Okay, so now it becomes an actual issue for me because X is resolved to be 0. Okay. So it looks like the assembler needs some debugging because it wasn't assembling the code correctly. X as a label should be a 1, not a 0, but somehow it was defined to be a 0. So this makes it even more fun because when you're making your own tools and you're the only one debugging the tool, then when something doesn't work, you don't know whether you make a mistake in the assembly code or you have a bug in the tool chain itself. That's kind of what I need to do in my first job or the job before I came here. I was maintaining a C compiler and also the library supplying to the C compiler. So when you're writing application code and it doesn't work, the bug can be in the code that you're writing, in the tool that you're using, but sometimes it's even in the compiler tool that I use to compile the program. So it can be any one of those things. So you just kind of have to go upstream, just step by step to check on things. Okay, so y is 0 and x is y plus 1. So that should have resolved correctly. But the symbol table tells me that it has not. Because this is x and there's no error. Alrighty, well, looks like I got work to do. The only reason, I think I know why. It's still an issue of the tool because x was defined twice. Okay, let me show you what I mean by that. See how is x defined here as well? It was defined twice, but the assembler did not check for that. So if I fix the program to use something other than x, it would have worked. So instead of using x here, and I use like main underscore x and use it consistently, then it would have worked. So right now, do not use the same, do not redefine the label twice, okay? Define the label up to once, because if you define the label twice, the second definition takes precedence over the first definition. Okay. All right. Well, that's the end of today's class. We'll head over to the lab. We do have some activity in the lab. So I'll see you guys over there. Let me close the log. This